So sorry to reiterate, but for the purposes of the recording, we've been starting in on a few more nucleophilic acyl substitution reactions. These are the ones we're going to cover today. We're starting out with ammonolysis of esters, and ammonolysis can be spelled either way. Both of these spellings are correct. But in general, the reaction entails treating an ester with ammonia. And the major organic product is going to be a primary amide, something of this type. And there is also going to be a side product of the alcohol portion of the ester that winds up in a molecule of alcohol. Almost certainly, that alcohol that you get will be either methanol or ethanol, since by far the vast majority of esters are methyl and ethyl esters. I would, at a conservative estimate, say that at least 97% of all esters are going to be methyl or ethyl esters. So that's going to be a byproduct. That's going to be removed from the reaction mixture. And what will actually isolate will be the primary amide. And so just to give an example, if we took ethyl benzoate and treated it with ammonia, I would expect to get benzamide. And you will get a molecule of ethanol as the byproduct. The amide carbonyl carbon used to be the ester carbonyl carbon. So these two will once again be corresponding compounds in the sense that the main carbon chains in both of them will have the same number of carbons in it. So, but the important point here is this is another nucleophilic acyl substitution reaction. You've got the alcohol portion of the ester and the ammonia switching places. And so effectively, the NH2 portion of ammonia switches places with the alkoxide portion of the ester, and you get the primary amide, plus as a side product, a molecule of probably methanol or ethanol. So that's just another reaction of this type. And you know what? I'm going to go a little bit crazy here. I think it'll make much more sense if I go a little bit out of order. Let me leave reduction of esters and carboxylic acids for the end, because that's actually a different type of reaction. That's more of an addition reaction. But let's cover hydrolysis of amides. And then I'm going to add a little bit of material that's bits and pieces taken from some of the sections that we're not covering. But I really think these ideas, at least, do need to be mentioned because they're relevant to the material and because they're just further examples of nucleophilic acyl substitution reactions. And then we'll go back and cover reduction of esters and carboxylic acids. If there's still time at the end, I still would like to review in the carbohydrates chapter, exhaustive alkylation versus glycoside formation. And if there's still time left on top of that, then maybe we'll review acetal formation, which was in chapter 9, and I think was one of the tougher topics in that chapter. So that's basically what I've got planned for today. So now that we've got an amide, I do want to point out, actually put this over to the side. I do want to point out that amides can be hydrolyzed, just like esters can, just like nitriles can. And this too is a nucleophilic acyl substitution reaction. And in general, if you take any kind of amide and you treat it with either aqueous acid or aqueous base followed by aqueous acid, you can do it either way, just like you can hydrolyze esters in either acid or base, you can hydrolyze amides in either acid or base also. And in the end, I would expect that you would get the corresponding carboxylic acid plus a molecule of ammonia. So let's look at a couple of examples of this type of reaction. If we took, for example, benzamide, this is an example also. If we took, for example, benzamide, and we treated that with dilute aqueous acid, we can expect to get benzoic acid as the product, plus ammonia. That's an inorganic side product. Or to do a slightly more complicated example, that's a 2. Let's say we took this amide and hydrolyzed it. Then I would expect that you would get, with dilute aqueous acid, I would expect that you would get this carboxylic acid. And this time the side product would be dimethylamine. So these don't have to be hydrogens on the nitrogen. They can be alkyl groups also. And in any case, you will, this is going to be essentially an inorganic or almost inorganic side product that will be water soluble, that will be removed from the reaction mixture, and the organic product that we would isolate would be the carboxylic acid. So this is yet another example of a nucleophilic acyl substitution reaction. You have the amine portion of the amide and the OH of a water molecule switching places. So it's again a substitution reaction. Remember, any kind of substitution reaction is going to involve two pieces switching places. That's the concept of substitution in chemistry in general. That's true of both organic and inorganic reactions. In general, you'll expect to see two things switching places. Good. Any questions so far on any of that? Well, let me erase my board then. I really, in many ways, prefer chalk on a chalkboard, but it is what it is. Because I prefer it when there's like multiple chalkboards and I can slide one up and slide another one down so people can still see. But this is, I suppose, the way of the future. Okay, so another type of reaction I want to mention is alcoholysis and ammonolysis of both acid chlorides and anhydrides. And the reason, there's two reasons I want to bring it up in the context of this chapter. First of all, because this is another important kind of nucleophilic acyl substitution reaction. And second of all, because we've already in fact talked about it. In the carbohydrates chapter, we talked about exhaustive acylation of a monosaccharide, and that is alcoholysis of an acid chloride. So I really wanted to put that concept together for you guys. So although this doesn't come from one particular section of the chapter, this is class material, and this is material that you will be responsible for on exam 4 and the final. So, and I think you'll find it fits right in. It's just another example of the same type of reaction. And alcoholysis of an acid chloride first requires an acid chloride, obviously. So here's our acid chloride, and then we will treat this with some alcohol. Actually, I want to make that another color. I haven't done much with colors today. That will really show off the substitution part of the reaction. And in the end, you will get an ester. Plus, I suppose, a molecule of HCl, which we really are much less concerned about. Similarly, you can do the same thing with ammonia. Make that another color also. and you will get an amide. Plus HCl. And both of these reactions you can also do on an acid anhydride, as we discussed in chapter 15, I think it was, the chapter on carbohydrates. You get the same products. In this case, the side product will be a molecule of the corresponding carboxylic acid. And you can likewise take any acid anhydride and treat it with ammonia, and you will get an amide. Wish I'd done the other examples like this too. It really makes the substitution stand out when you look at it that way. So just to give a couple of examples of each of these, if let us say we took benzoyl chloride and we treated that with isopropyl alcohol, you would get the isopropyl ester of benzoic acid. Plus HCl. Also, if you took acetic anhydride and you treated it with ammonia, well, I would predict you would get acetamide plus acetic acid. All of which, all four of these combinations are just more nucleophilic acyl substitution reactions. So it's not really a different reaction. It's the same type of thing. It's just you get slightly different products. But in both cases, or in all four cases, you will get a substitution product. So I really felt if I didn't mention these reactions, I'd be leaving really a huge hole in the chapter. And also, I want to emphasize again, when we talked about exhaustive acylation of monosaccharides, that's this reaction, except instead of isopropyl alcohol, it was several OH groups on a monosaccharide. But it's exactly the same type of reaction. In both cases, you can take either an acid chloride or an acid anhydride, react it with the monosaccharide, and you'll get esters of this type. If every single one of the OH groups that's on that monosaccharide molecule will be turned into an ester. And that's also a nucleophilic acyl substitution reaction. So since we really already covered this reaction, this type of reaction, in chapter 15, I figured it bore mention here. And I always like to make connections to earlier chapters whenever possible. And this is certainly one of those times when it's very convenient to do so. Good. I think that's about all I can think of to say about any of that. Questions on this reaction? Or these four reactions that are really all kind of the same? Yes. Yeah, and are the R's the same? Yes, and in anhydride, they're the same. I only wrote R1 and R2 over here to distinguish the R groups from the alcohol and the anhydride. But yes, there's no, like, if you mean in general, I don't know of any structural reason why they have to be the same, but I think in practice they always will be. I've never seen a mixed anhydride. So I don't think you're ever going to see anything where they're different. Good, other questions? Now I think it makes a lot more sense to cover reduction of esters and carboxylic acids. Because all of those reactions were of the exact same type. They were all nucleophilic acyl substitution reactions. This really isn't. This is more of an addition reaction. Could also consider it a redox reaction, since, as you see, it's reduction. So reduction of esters and carboxylic acids. In this case, the reagent of choice is lithium aluminum hydride, which is something we've met before. Back when we were talking in chapter 9 about ketones and aldehydes, we said for ketones and aldehydes, lithium aluminum hydride and sodium borohydride are interchangeable reagents. They will both bring about the reduction of the ketone or aldehyde. That is not true for esters and carboxylic acids, however, as we're going to see. And if you take a carboxylic acid, we'll just start with that. And we'll do, again, both the general cases and some examples. And you treat it with lithium aluminum hydride. I have trouble saying the name of that reagent. Then you will get the corresponding primary alcohol. And if you're wondering what happens to the aluminum, of course, it doesn't disappear. It just, you get aluminum salts plus aluminum salts. They're inorganic, though. And what had been the carbonyl carbon of the carboxylic acid becomes the carbon of the primary alcohol. And in fact, both of the hydrogens that are attached to carbon come from the LAH. We just call it LAH because it is hard to say. Lithium aluminum hydride. But the same is true of esters. And I should have said, since someone was asking about the R1 and R2 groups, they can be the same or different for an ester. But again, the reagent of choice is LAH, and you will get, as your organic product, the corresponding primary alcohol. The other product you will get is a small alcohol, which is almost certainly going to be methanol or ethanol, plus aluminum salts. So once again, the CH2 carbon of the primary alcohol had been the ester carbonyl carbon. So either a carboxylic acid or an ester can be reduced with LAH to give you the corresponding primary alcohol. Losing my mind. Oh, right. Another thing your book doesn't mention, but is a really huge hole, is that our other reducing agent, sodium borohydride, is not interchangeable with LAH for esters and carboxylic acids. Sodium borohydride does not react. Oh, well, before I get to that, I really should do an example. I was so excited about sodium borohydride not reacting. So let's look at some examples of this type of reaction. So if you were to take, let us say, benzoic acid and treat with LAH, you will get benzyl alcohol. And if you took this methyl ester and treated it with LAH, you would get this primary alcohol. Let me just point out where the carbons went. This carbon over here used to be the ester carbonyl carbon. And you would also get methanol, and in both cases, aluminum salts. But the major organic product in both cases will be a primary alcohol. So those are just some examples of the reduction of a carboxylic acid or an ester. For those two, LAH is the reagent of choice to reduce those down to a primary alcohol. And in both cases, that's what you'll get, is a primary alcohol. What I was starting to say, though, was sodium borohydride does not react with either esters or carboxylic acids. So you could take either a carboxylic acid or an ester. Your choice, take your pick. And if you added sodium borohydride, no reaction, NR. Nothing will happen. Doesn't touch it. So that means that if you had a compound that's both an ester or carboxylic acid and a ketone or aldehyde, the product of reaction with sodium borohydride and lithium aluminum hydride will be different. So let's say that we took this compound. That has both a ketone and an ester. If you were to treat this with sodium borohydride will reduce the ketone. That was part of the chapter 9 material, but it will not touch the ester. And I expect that the product you would get would look like this. And in this case, this secondary alcohol carbon used to be the carbonyl carbon of the ketone. But again, it does not touch the ester. It only reduces the ketone or aldehyde. If you took that same compound that looks absolutely dreadful. Looks slightly less dreadful. If you took that same compound and treated with LAH, then the LAH will reduce both groups. It'll reduce the ketone to a secondary alcohol and the ester to a primary alcohol. And in this case, the secondary alcohol carbon once was the ketone carbonyl, and the primary alcohol carbon once was the ester carbonyl carbon. So that's very important, that you can get different results if you have both functional groups in the molecule. And I don't love giving you extra material that's not in the book, but again, it's such a large hole. I feel it just has to be mentioned. Could it be on the exam? Yes. Will I ask 30 questions about it? I don't think so. I just wanted to give you a little more context on these reagents. Good, and I think that's about it for the rest of chapter 10. I do have a couple things I'd like to review so as to make good use of the class time. Any questions on LAH? Also, do these seem good to review? I thought that, question? Will LAH make no reaction? No, LAH will reduce almost anything. I mean, if there's a carbonyl, it will reduce it. If there's no carbonyl, I guess there's no reaction. But Do you mean, is there a compound like this for which LAH will say no? No, no, that's a very reactive reagent. It's good. It'll kill whatever it can get its hands on. Sounds very bloodthirsty, but I think you know what I mean. So do those seem like reasonable things to review? I figured I wanted to reiterate about the difference between exhaustive alkylation and glycoside formation in monosaccharides. And then we'll see if there's time left after that. Okay, so as you'll hopefully recall, since it's on the material for the exam, let's see if old Jack remembers how to draw a monosaccharide. We'll even do glucose, just because it's easy to remember. Recall that if we take pretty much any simple sugar in its cyclic form like this, in its pyranose form, and you treat it with pretty much any alkyl halide, preferably primary, but for our purposes, any alkyl halide. If you treated this with, let us say, 1-bromobutane in excess, so excess 1-bromobutane, and also for best results, you want some silver 1 salt, either silver 1 oxide or silver 1 nitrate. Then you will get the product of exhaustive alkylation. And all of those oxygens will go from OH to O alkyl. 1, 2, 3, 4. Let's see if I can do this tricky thing again. One, two, three, 4. 1, 2, 3, 4. CH2O, 1, 2, 3, 4. So that would be the product that you would get. And again, the key point here is that it uses an alkyl halide and a silver 1 salt in order to precipitate out the halide. In this case, you would also, your inorganic side product would be silver 1 bromide, which is a precipitate, insoluble. So that drives the reaction forward. In comparison, glycoside formation in the case of forming a glycoside, you use very different reagents. We'll even take glucose in the same anomeric form. I guess that would be the beta anomer because the OH is pointing up. And so the reagents you'll use will be some alcohol. Let's even go crazy and make it not methanol or ethanol. Let's take isopropanol and an acid catalyst. And oh, did I mess something up? Oh, I forgot something, didn't I? What's the, what, sorry? Silver 1 bromide, AgBr. Oh, solid. Let me try to make that actually legible. There we go. Anyway, I would predict that you would get the isopropyl glycoside, both beta and alpha. So that's only going to react at the anomeric carbon. And you would also get the alpha anomer with that alkoxy group pointing down. So this uses an alcohol plus acid catalyst. So this might say H2SO4, something like that. Who knows how Al will put it. But you could use a little bit of sulfuric acid or phosphoric acid or something like that. And in this reaction, the reason that you get both anomers is because the reaction actually occurs at the carbon. So reacts at carbon. Whereas up here, it doesn't react at the carbon. It only reacts at the oxygens. So those are the two main differences, I would say, between the reactions. And that's how you can tell them apart, I would say. But you need to be clear on what you're reacting the monosaccharide with. And it's a little confusing because in both cases you get acetals. In both cases you get ethers. But in one case it's exhaustive formation of ethers. And in the other case you just get the acetal. It's going from the hemiacetal to the full acetal. But those ideas, I think, will help you to distinguish them. And I think it's good to go over it again. I want you to have some benefit for coming to class, basically. So yeah, and that still leaves us with 10 minutes. We'll have plenty of time to go over acetals and hemiacetals again. Does that help? Does that help to distinguish those two types of reactions at all? I just want to make that clearer because I sort of was afraid that might be a little bit unclear. Maybe. Was I just talking about the differences between the reactions? Oh, well, you can see that in this case, you only get one anomer. If you start with one anomer, you only get one anomer. That's because nothing happens at the carbon. It's the oxygen that's reacting. Whereas over here, it actually is reacting at the carbon. So that's why you get both anomers. That's correct. In the glycoside formation, it's only the one change that's made. The other OHs are not touched. Yes. Does it have to be that specific carbon? Yes. It's only carbon 1 that reacts in the case of forming a glycoside. And no, you're fine. Oh, because remember, carbon 1 is the hemiacetal carbon. And so what we're doing is changing from a hemiacetal to an acetal. But the acetal can be either above or below when it forms. Because what happens is actually it opens back up to the straight chain form and then closes again. No, they're not the same thing. They're different compounds. And you do get both. So that's one of the differences between the reactions. See, I guess it is confusing. That's why I wanted to make sure to go over it again. But when you form the glycoside, you're forming the acetal, and you do get both acetals. They're not the same thing. Whereas with this, you're not reacting at that carbon atom. So you only get the one result. But it does react at all of the oxygens. Well, all of the OH oxygens. It doesn't react at this oxygen. No, it's a good question. Oh, I'm sorry.
Is the glycoside stuff like the alpha and beta?
Right. Let me get this right now. I guess this would be the beta one and this would be the alpha one. right? Alpha is down because we started with beta. Here, it's all beta. Nothing changes because, again, there's no reaction at the carbon. So that stays put. And that's actually, oh, other questions before I go on. That's actually an excellent lead-in to acetals and hemiacetals. So this was chapter 15 stuff. I'm going to go back all the way to chapter 9 now. It seems so long ago, but I thought it was 15 that was carbohydrates. No? I will be complete. Well, actually, I have my book with me. Maybe it's 16. I guess it is 16. 15 was lipids. You're quite right. It's chapter 16 is carbohydrates. I'll be honest, I left my lecture notes at home. That's why I quickly printed them out and jury-rigged something. So yes, that's chapter 16 on carbohydrates. So hemiacetals and acetals are formed by the reaction of a ketone or aldehyde with, I'll even use that same one again, an alcohol, probably a small alcohol, and an acid catalyst. This will also help explain why you got the two products before, because it's this type of reaction. And the first product is the hemiacetal. That's the addition product of one molecule of the alcohol. So you have O-alkyl and OH on the same carbon. And we define that as being a hemiacetal functional group. But then it will go on to react further. And you will get the full acetal. Which looks like this. So so there's also, you also do get a molecule of water out at the end. But then it can't react further. That's the final product. So in the case of the monosaccharides, we started with the hemiacetal and then made the full acetal with loss of water. The reason that the reason that we only get the one compound here is because it's not a chiral compound. We don't have like the alpha and beta thing going on. This carbon here is not chiral, so there's no issue of multiple products. But this is very analogous to glycoside formation. So that's something that this should be from chapter 9. I'm going to check myself since I don't trust myself. Yeah, 9 is aldehydes and ketones. Yep. So that's another connection that we can make. And actually, that's pretty well all that I planned today. Are there any other questions? I just wanted to pick some things to review that I thought were the toughest subjects in those chapters. But that's it. That's our last class before Thanksgiving. So have a wonderful Thanksgiving. As I said, I fully give you permission not to study on Thanksgiving or Black Friday. In fact, I almost wish you wouldn't. Save it for the weekend. And I will see you all Monday, a week from today, for our exam. I just noticed there's a question in chat. Oh, happy Thanksgiving. Same to you.